using the technique of partial fractions, integrate. So 6x squared minus 35x plus 45 up on top over x cubed minus 6x squared plus 9x. Okay, so we're in a good position. We've sort of got a quadratic expression up on top, and we've got a cubic on the bottom. So we're not going to have to do any weird reductions or rewriting. But what we should do, I'm just going to copy this down so I don't have to keep bouncing back and forth. So it's minus 35, and then it was plus 45, and then it was over x cubed. Was it plus 6x squared plus 9x? I think maybe it was minus. I think it was minus 6. It was minus 6. But okay, other than that, we're all fine. So we'll go back and we'll write minus 6x. Okay, so this is what we're trying to integrate. We'll just stick with our notepad here. Okay, so what should you do? Oh, this guy should be a square. What should you do when you come across this? Well, I see it's a rational expression, polynomial over polynomial, so immediately you should always, your brain should be trained at this point to think, okay, partial fraction decomposition, and even if we weren't thinking that, the question told us to do that, so that's really nice. So what do you do for partial fractions? Well, with this cubic down here on the bottom, bigger degree than the quadratic on top, the first thing we should do is factor this. So it's not too bad. I can see I can factor out an x, and then x squared minus 6x plus 9, and this I recognize as the square of x minus 3. So I've got a bunch of linear factors. I got x, and I've got 2 copies of x minus 3. This informs how I set up my partial fraction decomposition, okay, which is a way of rewriting this polynomial. Okay. So what do we do? So for x minus 3, so each of the factors gets a constant, but when you have a repeated linear factor, like the x minus 3, you have 2 constants, when you're repeating 2 times, one for just the plain old x minus 3, another for x minus 3 squared. And then there's only one copy of x, so x just gets its own little constant. So we should be able to find constants a, b, and c that make the left-hand side equal to the right-hand side. Now, just looking at this expression here can be a little overwhelming. So I find the easiest thing to do, and I always do this pretty much every time unless I spot some special trick, is I multiply both sides by the denominator over here, which we could, again, rewrite the way we have it. What that does is if I multiply everything here, some of the factors will cancel out with some of the factors that the denominator has. So like these x's will cancel out. These x minus 3s will cancel out. One of these x minus 3s cancels out here. And then we're not looking at big, scary rational expressions anymore. We've got one polynomial equal to another polynomial. So we'll have a x times x minus 3 plus b times x plus c times x minus 3 squared. Okay. So now we got to figure out the a, b, and c. If we don't have those constants, we don't have the partial fraction decomposition, so we can't actually do the integration with all our building blocks and stuff like that. So what do we do? There's a couple strategies you can use. With distinct linear factors, one thing you can often, not always, but often get away with is plugging things in. So for example, if I were to let x equals 0, then you'd get 45 on this side, and then a times 0, well, you wouldn't care about that. B times 0, you wouldn't care about that. And then you get c times negative 3 squared, which would be 9c. And then, okay, we could solve for c. So that is a strategy. And if you want to use that, I think that will work in this case. You will be able to sort of solve for everything after a little bit. But it's not the only strategy. So I'm going to actually use a different strategy just to practice or just to show it off here. Okay? Another strategy is to realize, hey, I've got 2 polynomials here. One of the nice properties of polynomials, and polynomials have tons of nice properties. They are just probably the best set of functions out there. But one of the properties of polynomials is that 2 polynomials are equal only if they have the exact same coefficients. So what I can do on this side is expand these out and say, okay, this is ax squared minus 3ax, right? When you multiply your ax's in here, plus bx plus c times x squared minus 6x plus 9. Okay. This strategy is useful when you have less linear terms. I mean, the plugging in specific values will work just fine here. But let's see, we've got a x squareds and we've got c more of them. B minus 3a's minus 6c's worth of x's, and then plus 9c. Right, so there we've collected everything together. So that polynomial with its a's and its b's that we don't know is equal to this polynomial. But as I said before, one of the nice things about polynomials is polynomials are only equal if their coefficients are equal. So 6 has to be the same as whatever a plus c is. All right, moving to the next one. Come on. Minus 35 has to be the same as b minus 3a minus 6c. And we'll use green here for the last one. Oops. 45 has to be the same as 9c. They have to be. And so we can use this to then slowly solve for a, b, and c a little more algebraically rather than just plugging in and hoping a bunch of things are equal to 0. So for example, divide both sides here by 9, and you'll get c is 5. Once I know c is 5, a plus 5 is equal to 6. Well, that means a has to be equal to 1. And now I know c is 5, so this is really minus 30. And a is 1, so this is really minus 3. So negative 35 is b minus 33. B has to be negative 2. And we find our constants this way. Okay? Could you do it the other way? Yes, of course you could. But this is another way, and it worked just fine. So what does it mean for us? Well, it means we've got the constants that we need for our partial fraction decomposition. So let's rewrite x cubed minus 6x squared plus 9x. And a was 1, so we had 1 over, I think we put the x minus 3's first, plus negative 2, x minus 3 squared, and then I think it was 5 over x. I'll just double check. One of the worst things you can do is jumble up your a, b, and c, because then you're not correct. But yeah, c was over x. Okay, so we're good. All right, so this is true. As long as you plug in an x where both sides are defined, they will be equal expressions. We're not interested in evaluating things. We're interested in integrating. So we can come along and we can integrate each of these pieces here separately. So we get the integral of 1 over x minus 3, minus 2, just bringing this guy out, 1 over x minus 3 squared. Oh, don't forget our dx. And then we can bring the 5 out, 1 over x here. And then each of these we can integrate fairly quickly. You can use, if you've got formulas memorized, that's great. If not, you can do substitutions. That's fine too. Depends on the effort you want to put in or what you want to show people. So minus 2 and then x minus 3 squared. So how does that, if I remember my formula, so minus 1 on top, the constant a, which is just going to be 1. It's 1 times x here, times 1 less than the degree. So that's 1. And then x minus 3 to the 1. So these 1's go away. This minus sign turns into a plus. And then the 5, well, that goes to ln absolute value of x plus a constant. So I'll put this as my final answer. So let's say 2 over x minus 3. Okay. Plus 5 ln absolute value of x plus a constant. And there we go, all nice and neat, all complete and done. There we go. We managed to integrate this rational function here using partial fractions.